Cool. Thank you, everyone. Again, my name is Jennifer Hobbs. I'm a senior data scientist at Stats. Briefly, I'll just kind of give you an intro to myself and our team, talk about the data that we have at Stats, and then really kind of dive into the tracking data analysis. I'm not going to kind of go into the details of the math. Mostly, I'd like people to take away kind of the value that we have in tracking data and what kind of types of interesting questions and interesting analyses tracking data allows us to do. And then kind of just a look beyond that. So tracking data is great, but like what's the next horizon beyond tracking? So this is our team at Stats. We're an international team. We're based primarily out of Chicago, but we have people in Europe as well as Australia. Team of I think 12 now, but continuing to grow. Just my background as far as like where I'm coming from. Again, I've spent almost 10 years at Northwestern in some field of science, culminating doing my PhD in physics, but really looking at computational neuroscience, so studying how the brain encodes touch. And it seems like that is a really nothing to do with sports or basketball in particular, but actually in some ways the math is identically the same. So a lot of my work was looking at how the stimuli of the environment could be captured by a neural spike. And you could imagine that's very similar to saying how could the movements of the players allow us to predict an event? Like was this a pass or was this a shot? Was it a pick and roll? And really understanding kind of the structure of the natural environment. So they seem like very disparate fields, but actually a lot of commonalities. And I've always had an interest in sports. Was involved in a lot of sports growing up. So when the opportunity came to come to Stats, I was really excited to join this team. Yep, so there you go. So Stats, we're really focused on driving machine learning through data. Stats has been one of the leading data provider internationally for collecting data for the past 35 years. And really we have a huge breadth of data from box scores to play-by-play and then to videos and tracking. So you can imagine with these three sources of data, they kind of span this spectrum. Box score data, it kind of has the least information or value. You have one line or two lines per game that kind of has an aggregated count of points or shots or rebounds. Then you have play-by-play in the middle. You have that kind of sequential nature, but again, it's a player took a shot from here, or this happened. And then really at this extreme end, we have the raw video, we have the player tracking. We know where the players and the ball are at every single frame. And so, our goal as part of the AI team is to maximize the value of sports data that we have, especially coming from over here, from the videos and tracking. I'm not talking that there's anything wrong with doing box score or play-by-play analysis. We actually do that as well. We had a paper at Sloan this past year, the Sloan MIT conference, looking at in-game win probability. So being able to factor in team lineup information and doing sequential prediction. We're actually able to get significantly, like here's kind of a baseline model out there. Here we're able to predict the outcome, the winner outcome, much earlier in advance. And actually the data set that was used for this is publicly available on our website. So you can go online, fill out a form. One of my colleagues gets an email asking, which he'll respond to, asking you to fill out an NDA and stuff like that. But you can actually kind of play around with this data online. We can also do stuff to look at a team style or strategy. So here for soccer, we're looking at how teams score goals. And this is all just from event data. What kind of events and what sequences of events generated shooting opportunities. But really what I'm going to focus on today over here is on the video and tracking information, and particularly with the tracking data, what is it? What kind of interesting questions can we answer? So yeah, what is it? What can we do with it? So really our tracking data, it's the XY positions of all the players, and then for basketball, the Z position of the ball as well. We also have the referees. For soccer, it's taken at 10 hertz. For basketball, it's 25 hertz. So this is a lot of data. Just from this information alone, you're talking 15 million data points a game just from the locations and the identities. But it's pretty limited in its raw format, right? If I were to just plot the locations of the players for the game, here's a basketball court, you might be able to tell that, and just dots of where everyone stands around. Players move, they do things, they interact, they make complex motions. And if we don't treat this data kind of appropriately, there's not a whole lot of interesting things you can do with that. So what can we do with it, and how do we have to interact with this data to draw unique insights? So a couple of the things that I'll show you today are going to be about automatic formation detection in soccer, transition analysis, which is work that I did for Sloan last year, expected goal value. Here, I'll show you an example from soccer, but we've done work for basketball as well. And then some work called ghosting that we've done with colleagues at Disney and Caltech. So automatic formation detection. If people are watching the World Cup right now, usually before the start of the game, you'll see everybody has some kind of, badge like this that says, all right, this is how this team is going to set up in this formation, and maybe their opponent set up like this. But obviously, players move around. Right, again, if I were to take each player and plot their, movement over the course of the game, they all run around, they cross paths, they don't stay in this nice, tidy format. So can we learn that formation from this mess? How do we do that? How do we actually determine how they're set up? And not just at the start of the game or when the ball is stopped and they're all kind of posing for the camera. How about when things really matter, when they're really moving around? And so what we can do is actually learn to detect these formations directly from this data. And this is through an alignment process where we look to find the formation that minimizes the overlap between the people. So at each frame, we can say what ordering of these players, which kind of slot do they go into that allows us to get this separation. And this is really coming out of an expectation maximization algorithm. So at each frame, we can process the game and say, okay, this player, even though he started over here, in this frame, he's really filling that spot. And this is important. It allows us to do just kind of straight out of the box, really interesting things like this, detect their formation, maybe detect their formation over the last 5 minutes. But also this alignment process is really kind of our bread and butter to do further analysis. So anytime you're doing machine learning, you need to have your variables ordered in an appropriate way. And so what way is that? What is that right representation to do your analysis on? And using this is really what allows us to do much of the later work that I'll show. So in addition to just saying, well, I just want to know what their formation is over the game right at a very point in time, can I actually look semantically? Can I use the context of the game and say, how does maybe the score impact how I set up? So again, here's for a particular team, for a particular game. Here you can imagine the center of each of these ellipses is their kind of mean position in their formation, and then the axes of the ellipse represent the variation, so how they're kind of moving around that central position. So here this is in this one game, the home team attacking, and you can see that when they fall back to defense, those outer players kind of step back into this more defensive, conservative position. And again, we can do this all automatically directly from the data. And here's their opponents, again, attacking and then defending. And so as opposed to having to have somebody sit there and hard-code it or just say, well, if you're always a right back, you're a right back for the entire game. Here we can account for the fact that there is variability, there is permutation, there is movement throughout the game. So now that we have this, we can start asking interesting questions, like how does a team's formation impact its scoring opportunity? In the Premier League over the past couple years, there's been a lot of changes as far as you play with essentially like 5 defenders or 4 defenders. And so one of the ideas behind that is that having the extra defender prevents being counterattacked against. And so a lot of teams have switched to have that extra defender there. So can we actually start to investigate things like this now that we know how a team plays at a particular possession of the game? And so some work in transition analysis that we did recently was to understand what do teams do immediately after they regain the ball. So why is this important? Well, right after a team regains the ball, this is really the opportunity where they have to take more shots, just in general, higher quantity of shots, as well as better shots. So not only are they taking more shots, the shots they're getting are of higher quality. And so this is really a period of time where we see this is really a real critical phase of the game. Can we understand it more? So again, we have our tracking data. So here we have Chelsea versus United, I think 2 seasons ago, attacking left to right, and in a counterattack phase. And you can see the trails of the trajectories after the regain, leading up to a shot. And the shot that it generated was high quality, had about 23% chance of being made, average shot is only around 9%. So again, the shot opportunity that this play generated was very high in quality. And so how can we understand that? How can we actually understand how this and this phase of play impacts the outcome of the game? Because if we look at this game, they both had the same number of transition opportunities. They both had the same number of shots off of transitions. But Chelsea was able to score on the counterattack, these fast, aggressive plays, much more effectively than United was in this case. And we can then also look, going back to the formations, to say, all right, when a team is in their formation, they're set. But as you saw, there was a kind of an offensive set and a defensive set. How long does it take for them to recover back to that position that they really want to get into? And then we can use that to analyze how long it takes them to recover. Were they out of position when the shot occurred? But this is really hard, because what is a counterattack? Is it a fixed amount of time right after they regain the ball? Not really, because if you regain it close to your goal, it's not going to take very long. Or you could have one that develops. Sometimes you see them start and kind of stall and then start again. It's not just as easy as defining a set of rules. So can we learn this directly from the data? Can we actually detect counterattacks without even any human labels? One of our original thoughts was that some of our team members who are particularly good at this were going to look at a bunch of examples and label them counterattack, not counterattack. But we couldn't even get great consensus around a bunch of experts. Some of them go, well, it kind of is. It's like, I can't build a model against kind of, right? We need is or is not. And so, all right, this kind of approach isn't working. Can we learn it unsupervised? Can we learn it right from the data? So the approach we use goes back to that notion of aligning. So we're going to align the players into their formation using like a 10-second trajectory now. So over this window of time, kind of what formation were they in, then cluster those trajectories. So literally we're clustering, ignoring the goalkeeper here and looking at one team at a time, clustering that 100-dimensional vector, and then realigning the players, and then repeating this process. And what this allows us to do is essentially find a tree of plays. So you can imagine all plays existing up here, and then I just say I want to break them into groups. I want to see plays that exist over here, plays that exist over here. And so I'll blow these up in just a second. Let me actually do that now. So if you look at any one of these, blue team is defending, red team is attacking upward, and you can see that kind of central formation of each player, as well as their kind of average path in that playbook entry. And so as we keep just doing this clustering and aligning until we reach some kind of minimum threshold, what it leaves us with are these leaf nodes that have spatio-temporally related plays, essentially. And even right now, we can start to do some kind of interesting analyses. So if we take a look at these two nodes over here, you can see that this is immediately after regain. They've regained the ball, maybe already kind of near the goal they're attacking, and they turn and they continue to attack right away. So we can kind of, just from the spatial signature, start to identify these as counter-repress events, which is, again, something that's become more in vogue in the past several years. The other interesting analyses we can do is say, all right, let's treat these all as, again, as plays in our playbook. And let's describe a team by how often they run each one of these plays, or how often each one of these plays is run against them. So I can imagine that I process a game, I code every single play after regain into one of those 14 bins, and then I just histogram it out. And I use this vector to describe the style of my team, that certain teams like to play in these kind of nodes, certain teams like to play in those. And then I can use that to describe a team when they're attacking and then when they're being attacked. And then here we've used a nonlinear embedding technique known as isomap. Think of it as finding points that are close in this high dimensional space as being close together and projecting it down to 2 dimensions. So usually like the picture that you'll see is like a sphere kind of being flattened. So teams that are very similar, in order to just kind of visualize it, wrap your head around it, teams that are very similar up here in this 14-dimensional space should kind of group closely here 2-dimensionally in a way that we can ingest it and kind of understand what's going on. So it gives us an idea of which teams have certain styles, both attacking as well as defending. So that's great. We've already kind of learned a lot about the different teams, but our goal again is to identify these counterattacks, these really aggressive styles. So what we did next was say, well, we have these nodes that have spatially similar characteristics, but are they semantically meaningful? Are they similar in other ways? So we have a different model, kind of standalone model, that looks at shot probability. So given the event sequence and the location of the ball, what's the likelihood of a shot being taken in the next 10 seconds? So I can imagine over that 10 seconds getting a trace of that threat, that dangerousness. And then again, for each play, I can go ahead and subcluster each of those nodes into one that's aggressive, that has a shot probability that continues to increase and get more and more dangerous, and then one that doesn't. And when I go through and look at each of those clusters, and then look at the pink subclusters within them, if one exists, I can say, all right, well, these pink ones, they're headed towards the goal, and they continue to get more and more dangerous. So we can identify these just from the data as our counterattacks. And what's kind of gratifying is that this occurs about 10% of the time, which is just what you would expect, kind of from our other knowledge. And again, looking at those particular plays, we see them having a higher expected goal value, higher risk, and a lot of other characteristics that you would attribute to be counterattacks. So another thing that we can do with the tracking data is to look at expected goal value. So again, expected goal value just being given a shot, what's the likelihood of it being scored. So you can imagine somebody hand labeling these, but again, we want to just go ahead and learn this directly from the data. So we want to estimate the shot quality directly from the data. I'm going to go ahead and skip this so I can actually show the last one. So here we've been doing prediction, predicting events, predicting kind of at a high level, but can we actually predict player motion directly? So a couple years ago, there was this article in Grantland about the Raptors doing something called ghosting, where you could see the offense in blue, the defense in white, and then kind of the open circles being these ghosts. And people thought this was kind of learned, from the data, but actually they had a bunch of coaches and analysts go through and label where the defense would have been. And that's obviously very time-consuming and labor-intensive. So can we learn this directly from the data? And so work that was done originally in soccer, here we have red attacking left to right, blue defending, white being these ghosts. And here we've learned the positions, this kind of average position of the defenders directly from the data. So here we're using some deep learning techniques to just feed in the data and be able to predict, given the hundreds of games that you feed in, can you predict where the defense would have been? And so I'm not going to step through this now, but the real kind of key behind this is, again, how we represent the data and then passing it into a deep learning model that can do this temporal prediction. And this allows us to ask interesting questions like what-if scenarios. So here initially we can train it on all the teams and say how would the average team have performed, but what if we only train it on the best 5 teams in the league? How does the scoring opportunity change? How would they have moved and positioned themselves differently? And again, same thing that we can do for basketball. So you see the actual defense and the opportunity it led to, and then say, well, actually, if I know how good a possession outcome of possession quality was, can I actually train the defense to move such that it minimizes the offense's opportunity and actually learn this kind of gold standard defense? Skip over this last example. And so tracking is great, but it doesn't tell the whole story. I'll just kind of close on some this last little bit. So here you see a shot go, or a pass go to the will-be shooter out here. He kind of waits, the defender closes out, and then he shoots. So what's going on here that he would have waited to take that shot? And if we actually go back to the video, we see what happens. Play sets up. Pass comes, it's a bad pass, and that's what allows the defender to close out. So the tracking allowed us to do some of this great analysis we saw earlier, but we can't get all of the complexities that we've seen here. So what's the next step? Where do we go from here? And so this is some work that was done with an intern, Pana Felsen, 2 summers ago, where we're actually able to get the pose of the skeleton. So as the player moves, we're actually able to detect the joints and get the shooter's motion there, and even extract away the shooter's form. But kind of like tracking raw points alone, isn't valuable. We need to kind of analyze this and synthesize this to do interesting work. And so we can break the shot into different phases and then go ahead and compare players based on what their motion looked like when they made versus when they missed shots, and really start kind of digging into the meat there. So just kind of in conclusion, tracking data has really kind of revolutionized the way that we understand and interact with sports. But this is just the beginning, and there's really a lot of interesting opportunities that are coming with a lot of the advances, particularly in deep learning, that exist out there. And then there's our website. Again, there's an interesting play-by-play data set that was used for the win probability people might be interested in. Also, the data that was used for that soccer ghosting work is up there. There is another basketball data set. It's more challenging to work with. My suggestion would be to take a look at those first two if you're kind of interested in playing around with it for some personal exploration. Alrighty, thank you.
We have time for some questions.
Yeah.
So on the gold standard defense, that was really interesting. I'm curious if there's like a next step, which is translating to like, because that's like a 2-dimensional high level, so trying to translate that effectively to the players for here's how you'd want to act now, and how they could recognize that on like a 3-dimensional plane easier in game.
You mean like with the actual like?
Yeah, like you've done the data analysis and have it, and you've got the gold standard defense, and I'm wondering if like you've gone to the next step of how you would take that and give it to like an NBA coach and say, okay, here's how you translate it to your players to know what they should do and what to look for.
Right. So even this in the Sloan conference back in this year with work that we did with again with Disney, it was a finalist there. The name of the paper is called. I can't say it. It's like Be Ghosters. It's supposed to be Ghostbusters, but it's reversed. If you go to our website, you'll find it. But the idea there is that a coach could actually take a tablet, draw out a play. You could synthesize the motion of the play from the sketch, and then from that, do the ghosting and say, all right, I would expect the defense to run this against the offensive play that you sketched there. So that's kind of moving
awesome.
and on a tablet so that you're not carrying a server around with you, right? So it's in a coach's hand, as long as he doesn't throw it on the ground.
Clipboards.
Right, yeah. That'll take some training.
Are entities like Chelsea and Man U, are they current clients of Stats?
We have a variety of different clubs. Sometimes it's league, sometimes it's kind of say like generic club relationships. Some of them we have very close relationships too, where we might roll out something, have close contact with them. I don't know who's at what level of, but yeah, there are clubs we work with directly, there are leagues we work with kind of broadly, and then there's just there's a variety of engagements.
I was just wondering, since you use them in the example, if they are a current client of Stats, Chelsea and Man U. Or
yeah.
What are some examples of clients? Are you able to share?
I don't know.
That's okay.
I mean,
I was just wondering, they have the money to pay you for the data, the knowledge.
Sure,
to
and
help
there's
them.
there's again a number of teams again across a variety of sports that we will do kind of one-off right now that we would do work with. More broadly, we're trying not to so much answer specific questions for teams, but like if this is something that a team is interested in, we'd like to work with them to build that technology out broadly. Because if it's interested in them, it's probably interesting to a lot of different teams.
Do you have any American football contacts?
Yeah, actually.
Seems the tracking would be ideal for that.
Right, and I know we do here. I again, I don't know the scope of the business, but like we were at I went to see our operations run at like a fire day last year. But yeah, again, a number of teams that were either in venue or partnered with.
One more?
Oh, so when you're looking at your counterattacking data, and you're trying to determine like what's the best counterattack, are you also looking at? I assume you're also looking at shot placement, of, like where the shot goes, because like team could take a shot from like 40 yards away, and it will be not as effective. Like even though it takes more time to get down the field.
Right. So like looking at different phases of the game. So here it was just a matter of like let's look at that first phase and see what gets generated out of it. There's certainly the idea of like a secondary attack comes through. Can we dig into that? And we haven't done that yet, but that's certainly, this is kind of step one, and then we have the pieces to assess the quality of the shot, and then we can kind of step forward from there.
Yeah, because like expected goals looks at the shot placement, so that's what I was wondering.
Yeah.
Thank you, Jennifer.
Yep, thank you.